All right. Question 9b, electronics. All right. First one. Why field effect transistors FET are called unipolar devices? Why are they? What are the charge carriers contributing to the operation of FETs? Right. The reason to say unipolar devices is only one type of carriers are contributing. Right. In bipolar transistors, both types of carriers are contributing. So here only one type is contributing. So A part 1. Sorry. Since only one type. Uni means one. Uni means one. Since only one type of carriers are contributing the operation. Right. It asks, what are the charge carriers contributing to the operation of FETs? In FETs, only one type. In the sense, if there is an N channel, only electrons are contributing. If there is a P channel unipolar transistor, only holes, protons are contributed. Right? Only holes. Which means this has to be either electrons or holes. Right? This is very important. It is electrons or holes. You can't say electrons and holes because in bipolar transistors both types are contributed as magnetic carriers and majority carriers. But in unipolar transistors there is only one type is contributing. Right? If there is a N channel, only electrons are contributing, and if there is a P channel, only holes are contributing. Second one, part 2. State why FETs are also known as voltage control devices. Right. So again, the basic segregation is bipolar transistors. Bipolar means NP, NP, NP. They are called as current control devices. And FETs are unipolar transistors. Unipolar transistors are called voltage control devices. The reason is the current through the device, current in the device is controlled by the voltage difference between G and S. G and S means what? Gate and source. Right? Because current in the device is controlled by voltage difference between what? Gate and source. That is also called VGS. Right? That is also called VGS. Next, part 3. We'll do here. Part 3. Calculate the drain current ID and the gate source voltage VGS for the circuit shown in figure 1, assuming VD equals 5. Okay. Let me copy it down first. Our circuit is given. Now this is actually a voltage divider of a FET. Right? This circuit is called the voltage divider circuit of a FET. This is called a voltage divider circuit of a FET. 2.2 mega ohms, 10 mega ohms. VDD equals 9 volts. VDD equals 9 volts. And RD 2.2 kilo ohms. And RS 1 kilo ohm. This is RD, this is R1 and R2. Right. So if VDD is given, one important thing, if VDD is given, which means the terminal here is grounded, because VDD is the potential low voltage of the battery connected between this point and the above point. So when that is grounded only, it is said as VDD. It can be considered as VDD. Right? So therefore, even though the grounding is not given, you have to consider the grounding. So here it should be grounded, right? It should be grounded. That is important. That is important. Right. First question is calculate the drain current ID. And another hint is given VD equals 5. So we know this is gate. And this is the drain. And this is the source. Right. And this point is also given. So which means this VD equals 5 volts. Right. Now if I mark the current flow here in the circuit, in unipolar transistors, there's no current flows, right? In unipolar transistors, there's no current flows through gate terminal, right? The only current flows through drain and source, right? High voltage is at here 9 volts, low voltage at here. So current flows downwards. Current flows downwards starting from here. This is ID and this is called IS, right? And in unipolar transistors, always ID equals IS, right? When we need to consider that ID equals IS, we will consider, right? First we need ID. First we need ID. Right. So apply V equals IR for 2.2 kilo ohms. See, very easy. By using V equals IR for 2.2 kilo ohms. 2.2 kilo ohms. Right. So we know V equals IR. Then V is voltage difference. That is VDD. If this is VDD, we know this point is also VDD. Up to here, that is VDD. Right. Up to here, that is VDD. So that is VDD minus VD. VDD minus VD, potential difference, equals ID RD. Plug these values, VDD 9 minus VD 5. We need ID and RD is 2.2 kilo ohms. 2.2 kilo ohms. Right. So ID is 4 over 2.2 10 to the power minus 3. So which means simplify this value. 4 over 2.2. Value 4 over 2.2. 4 over 2.2. 1.818. That is 1.818. 10 to the power minus 3 means milliamperes. So you can round this up. That is 1.82 milliamperes. 1.82 milliamperes. Right? So part 1 is done. Part 1 of the question is done. Next one. Next. And gate source voltage VGS for the circuit shown in figure 1. VGS. Right. To determine VGS, first we need to determine VG. Right. To get VG, here, if you mark these currents, see, let's say this current flow is I. Since there is no current through the gate terminal, same current flows through R2 as well, which means R1 and R2 are in series combination, right? So considering that they are in a series combination, we can use voltage divider for R2 and determine VG. If this is G, we know this point is VG, right? So the argument is since R1 and R2 are in series combination, right? Using voltage divider, by using voltage divider, or it is also called potential divider, by using voltage divider for R2, right? Potential across R2, now if this is grounded, this is also 0, right? VG minus 0, potential difference across R2, VG minus 0. Total potential difference across the system, VDD minus 0. Total potential difference across the system, VDD minus 0. Over addition of resistors R1 plus R2. If we are using potential divider for R2, multiply it with R2. Right? So we need VG. VG equals, VDD is 9 over R1 plus R2. I'm not going to convert mega ohms because it is going to be cancelled. 10 plus 2.2. This is 10 plus 2.2 times 2.2. So this should be simplified. 9 times 2.2 over 12.2. What's the value? 9 times 2.2 over 12.2. What's the value? It is 1.62. 1.62. So that is 1.62 volts. 1.62 volts. Now we need Vs, because to determine VGS, again we need Vs. And there is another proved equation as VGS equals minus IDRS for FETs, unipolar transistors. But if the unipolar transistor is in voltage divider circuit, that cannot be used, right? For other cases, it can be used except voltage divider, not for the voltage divider, right? Keep that in mind. Keep that in mind, right? Then to determine Vs, we can use V equals IR. Vs, we can use V equals IR for RS. Okay. We'll do here for next one. By using V equals IR for RS. Next one. By using V equals IR for RS. Right? So V potential difference is, now if this is S, this is Vs. Right? This is Vs. Vs minus 0. Vs minus 0 equals Is Rs. But we know for a unipolar transistor FET, always ID equals Is. Always ID equals Is. ID equals Is. Right? So Is is known. ID is known. Right? Then Vs, we need Vs. Vs equals Is. It was 1.82. It was 1.82 milliamperes 10 to the power minus 3 into Rs. Rs is 1 kilo ohm 10 to the power 3. Which means Vs equals 1.82 volts. 1.82 volts. Now our final target is what? VGS, right? So we all know that VGS can be written as VG minus Vs. VGS can be written as VG minus Vs, right? So VGS equals, VG is here 1.62 minus Vs, Vs is here 1.82, right? 1.62 minus 1.82, VGS is minus 0.2 volts. Minus 0.2, right? So part A is done. Part A is done. Let's move on. Part B. Part B. Part B. It says in the op-amp circuit shown in figure 2 is electromechanical switch SI, I equals 0, 1, 2, 3, right? Is operated by applying an electrical signal DI, I equals 0, 1, 2, 3, which can be high 5 volts or low 0 volts, right? When DI is high, the respective switch SI will be closed. When DI is high, the respective switch SI will be closed, right? When the switch is high, when the signal for DI is high, high means 5 volts, the switch is closed. Closed means switch on, right? And otherwise, it will be open. Open switch means switch off, right? When D2 is high, find the current through the resistor 10R in terms of R. Okay, first let me copy this down quickly. Okay, this is directly grounded. Plus Vs minus Vs. V out. V out is given. V out. And here some grounding is also given. Right? So V out is actually measured here. Right? And VSC is given as VCC in this case. Right? Minus VCC. And about this, how many resistors? 1, 2, 3, 4. 4 resistors with the switches are given. 4 resistors with the switches are given. Right. For this one, the respective switch is S1. Okay. S1. Right. And here another one. S0. S0. And 2 more resistors with switch. Right. And another one here. You can't see the board. Wait. Now, okay. Right. Okay, and this is at 5 volts. This end is at 5 volts. Right? This end is at 5 volts. And switches are S0, S1, S2, S3. Now, respective connections from D0, D1, D2, D3 are also given. I didn't draw because now the use of the switch is to whether it's high or low. If it is high or low, accordingly the switch will be on or off, right? So that we will consider. 40R, 20R values, 40R, 20R, 10R, 5R, 10R, 5R, and 8R here. 8R here. Right. If you can't see this 8R, let me write it below. 8R. All right. And current capital I is also marked here. A current capital I is also marked. All right. All right. First one, when D2 is high, if D2 is high, what happens is S2 will be closed. If D2 is high, so like this, S2 will be closed. S2 will be closed. Find the current through the resistor 10R in terms of R. Okay. Current through resistor. Let's consider that current as I2 like this. Let's consider that current as I2. Right. Now we know this is called V1 of a op-amp. V1, non-inverting voltage. And this is called V2 of an op-amp, that is inverting input voltage. If the op-amp is feedback means connecting, the process of connecting output with the input, right? If the op-amp is feedback, we know according to golden rules, it says V1 equals V2, right? So that I need to mention here. Because that is one of the arguments we are going to use, right? So V1 equals, V2 equals 0 volts, because this is grounded, that is 0. The reason is golden rules, right? The reason is golden rules, right? Or else you can say feedback rules, right? Golden rules or feedback rules, right? Now, if V2 is here, now up to this point, that is V2, no? So we know all these points are also V2. All the points are V2. If this is 5, all these points are 5 because that's the same wire. All these points are 5. That's the same wire, right? Now, if you need the current through 10R, apply V equals IR for 10R, right? Using V equals IR, this is part 1. Using V equals IR for 10R, right? V is high voltage, low voltage, it should be, right? High to low, current flows from high to low, so V2 minus 5 volts. It should be V2 minus 5. V2 minus 5, right? Equals I2 and R is 10R. We know V2 is 0. 0 minus 5 equals I2 times 10R minus 5 equals I2 times 10R. Minus 5 to 10 cancels. So I2 equals minus 1 over what happened? 0 and 5. It's given as minus 5. Sorry, it's given as minus 5. That's why. It's given as minus 5. Minus. Right. So that is given as minus 5. Minus 5. So this is plus 5. Right? Plus. So I over 2R. Current is I over 2R. Second one. Part 2. Part 2. When, if the set of voltages 5 volts, 0 volts, 5 volts, 5 volts, is applied simultaneously to operate the switches S3, S2, S1, S0, S0 respectively. Calculate the current I indicated in the figure 2 in terms of R. Total current is asked. Total current is asked. Now, how the switches are given? 5, 0, 5, 5. Right? Switches are given as 5, 0, 5, 5. Right? And for S3, S2, S3, S3, S2, S1, S0. Right? So which means S3 is closed now. S3 is closed now. And S2 is open. S2 is open. S1 is closed and S0 is closed. Right? So that is how the functioning of the switches changes. Okay, we need current. So let's assume these current flows as I3, I1 and I0. Right? Okay, now what we can do is, can you see that these three resistors are in a parallel combination because they are connected between -5 and V2. Right? These three resistors are in a parallel combination. So easily, what we can do is, first I am going to find the equivalent here. If the equivalent is known, right, total current which goes into equivalent should be capital I. That is one way of doing it. Or else, what you can do is, you can apply V equals IR 1 by 1 for 5R, 20R and 40R and determine simple I3, I1 and I0 and get the addition. That is also fine. Right? So I'll be using the equivalent resistance. Right? See, since 5R, then 10R, 20R, 5R, 20R and 40R are parallel. The equivalent is 1 over RE equals 1 over 5R plus 1 over 20R plus 1 over 40R. Right? So 1 over RE equals, we know 40R will be the common denominator. 40R will be the common denominator. 40R. Right? 5 times 8. 20 times 2, 1. So 1 over RE equals 11 over 40R. So RE equals 40R over 11. If equivalent resistance is known, now considering that equivalent resistor, we can use V equals IR. Right? Now, use V equals IR using V equals IR for RE. Right? V is again V2 minus 5. V2 minus 5 equals I, capital I comes because the total current goes through the equivalent resistor, I, RE. Right? So this is V2 is 0, minus 5, answer is 5, equals I times RE 40R over 11. 40R over 11. 5 times 8, which means capital I equals 11 over 8 tar. 11 over 8 tar. That is determined. 11 over 8 tar. Part 2 is also done. Right? Part 3. It says calculate the output voltage V out when a set of voltages again. Okay. I'll be erasing this. Right. Now what's the set of voltage? 5, 5, 5, 5. Which means all are at 5, all are high. High means all the resistors are going to function now. Right? Calculate the output voltage V out when a set of voltages 5 volts, 5 volts, 5 volts, 5 volts is applied simultaneously to operate switches. So all switches are going to be on now. Now this should also be on. Right. Now calculate the output voltage V out. Okay, calculate the output voltage. We need V out. Okay, again to determine V out, first we need capital I. Right? The new capital I. To determine new capital I, we need new equivalent. Right? I need new equivalent. So therefore, let's find the new equivalent again. Right? 1 over RE again for part 3. 1 over RE new one equals 1 over 5r plus 1 over 10r plus 1 over 20r plus 1 over 40r. 1 over r equals, common denominator is 40r, right? Here 8, 4, 2, 1. 1 over r equals 8 plus 4, 12, 14, 15. 15 over 40r, right? So r equals 40r over 15. 40r over 15 means by 3 we can cancel this. By 5 we can cancel this, right? By 5 times 8. 8r over 3. 8r over 3. 8r over 3. Now if there is known, to get V out, apply V equals IR for 8r. Yeah, let's see. I'll be erasing this. Right, now using V equals IR for 8r. See, using V equals IR for 8r. Right, now if this is I, current flows in this direction through 8r. Right, if that flows to the left direction, 8r. This is at V out and current flows from V out to V2. So this should be V out minus V2 equals capital I, R is 8r. Right, V out minus V2, we know V2 is 0, and I, new I is here, sorry, new R is here, new R is here. Only the equivalent resistance is known, which means I should be determined, right? So first let's determine I. First let's determine I before this. Here, then what you can do is, using V equals IR, using V equals IR for RE again, right? Then from here to here, again, V2 minus 5. V2 minus 5 equals IRE. Same thing, same application as before. Same thing, exactly the same thing. V2 is 0. 0 minus 5 equals, we need I now. And RE is 8R over 3. 8R over 3. Right. So 5 equals I times 8R over 3. Nothing cancels. I equals 15 over 8R. New I, 15 over 8R. Now I can use that value here. New I is 15 over 8R times 8R. It cancels. So 8R to 8R cancels. V out equals 15 volts. Final answer. V out equals 15 volts. If you understood the question properly, right, very easily you can get this 10 marks. Now for part 1 also, part A. For part A also it was 10 marks, and this is part 2, part B. For part B also it's 10 marks. And part 3 is a digital part, and for that digital part also that's 10 marks. That is how 30 marks are allocated here in this question. Let's move on, part C. Part C. Part C. A cash operated snack dispenser will provide a pack of Marie or chocolate cream biscuits under the following conditions. 1. The correct amount of cash is inserted. I. Second one, Marie M or chocolate cream C is selected. Then next one, if Marie is selected, availability of Marie in the dispenser X. Right. If chocolate cream is selected, availability of chocolate cream in dispenser Y. Right. Let's see. First one, obtain the logic expression for the condition under which a pack of biscuits may be obtained. Right. Part C. Right. Now about the electronics question, students, listen. About the electronics question, some students are, some in the sense actually the majority of students are not taking electronics question because of the lack of theory knowledge and all that. But in reality, compared to electricity, right? Compared to electricity, Usually electronics question is easier. So therefore scoring 15 marks in a question, as a question like, for a question like electronics will be easier compared to electricity. In electricity questions, the theory parts are higher and usually simplifications are also there and lengthier questions are lengthier. So it takes more time. But when it comes to electronics questions, usually when it comes to electronics questions, they don't have that much of simplifications compared to electricity, and the theory knowledge you need is comparatively less compared to electricity. The thing is, since electronics are covered at the last moment in most of the theory classes, most of the students are not familiar with the electronics theories, right? Most of the students, majority of the students are not familiar with electronics theories. So that's the apparent reason I see not to take electronics question in the essay question, but otherwise that's a potential question that you all could try, because scoring from the electronics question is easier, right? Either 30 out of 30 or let's say like beyond 25, greater than 25 from 30, that's a good mark. Scoring that is easier, right? So in that question, in this question also, we can clearly see the difference, right? See, obtain the logic expression for the conditions under which a pack of biscuits may be obtained, right? Now, if you can see a sequence of actions here, if you can see a sequence of actions to be performed, like a completion of actions one by one. Now, as an example, without inserting cash, we won't go forward, right? Because first step is inserting cash. So that is in a sequence. That is in a sequence, right? So therefore, without drawing the truth table, without developing the truth table for all the values, now I'm going to just check the availability and the sequence and come up with the final output. Now, otherwise, if you write the truth table also, you can write the truth table, but there will be more lines which are excluded, because now, as an example, if correct amount of cash is not inserted, right, then all the lines with zero cash will be omitted, right? Will be omitted from the truth table. So likewise, some lines are going to be omitted. So therefore, I'm going to focus on acquiring a biscuit here, right? Obtain a biscuit here, right? So first thing is to obtain a Mari. Let's think of this incident separately, because the reason is obtaining Mari is totally exclusive from obtaining a chocolate cream, right? They are two mutually exclusive incidents, right? So therefore, to obtain a Mari, see, I'm going to do this way. To obtain Mari, right? Let's say IM, sorry, let's say FM, right? F output M. To obtain a Mari, right? Correct amount of cash should be inserted, I, right? And if you have sequences, it always goes as dot functions, because now it goes as correct amount of cash is inserted, and then Mari should be available, and means dot. Mari should be, sorry, second one is Mari should be selected. So then Mari should be selected, and Mari should be selected, which means M dot M, and Mari should be available. If Mari is selected, Mari should be available. If Mari is selected, Mari should be available. N X, right? If IN, MN, X are satisfied only, we can obtain a Mari biscuit. So they are N connections, right? If either of the conditions can be satisfied, they are called O connections. Then it will be connected with plus. Now it is I dot M dot X. To obtain a chocolate cream, let's say FC. Similarly, you can write the expression again. To obtain a chocolate cream. Again, correct amount of cash should be inserted, and chocolate cream should be selected, and chocolate cream should be available, right? Now, the question asks, is obtain the logic expression for the conditions under which a pack of biscuits. Pack of biscuits means any pack. Either Mari or chocolate. Mari O means plus. Mari or chocolate. O means plus. The final output, Mari or chocolate, which means FMO, O means plus, FC. right? So F equals, Fm is Imx plus Fc is Icy. So you can see I is common, take I out, then Mx plus Cy. This is the final answer. C part 1. C part 1. See, if you understood what's going on here, easily you can write this out. Part 2. Part 2. Show how this may be implemented using logic gates. How this may be implemented using logic gates, right? Now, for this given output, show the logic gate, right? Very easy. We have how many inputs? 1, 2, 3, 4, 5. 5 inputs, right? Yeah, 5 inputs. So, we have to have 5 inputs. 5 inputs. 1, 2, 3, 4, 5. What are the inputs? IMX, CY. IMX, CY. Right? Okay. First we need MX and CY. MX and CY. Take M from here. Take M from here. And X from here. Right? MX. So connector and gate. Now as the output, M comes here, X comes here. The function is dot here. So MX comes as the output. Then I need to create CY. Take C from here, right? Take C from here. See? Take C from here and Y from here. Connect and AND gate again. Connect and AND gate again. Then from here C comes, from here Y comes. CY comes out. And take the addition. For the addition, you can connect a OR gate, right? Take these two wires and connect OR gate here. OR gate. Now after this OR gate, the addition of these two comes. Now here this is actually MX plus CY. The addition comes. And that addition should be dot with, this is a dot with I. Right? Dot with I. Then take this I. Take this I. Like this. You can take this I. And this output should be connected with another AND gate. This output should be connected with another AND gate. I dot this whole thing. Now this comes here from here. So here, this is the final left. This is the final left. Right? The expected logic circuit is this. Right? So even if you don't use the vertical wires, that is totally fine. Right? Usually when we draw digital circuits using vertical inputs, vertical wires as inputs is easier because you can expand the circuit horizontally or vertically as you wish. So that's why as a habit we draw vertical wires. Right? This is the circuit. This is the circuit. See how easy the question is. For this also 10 marks. Right? So easily 10 marks are gettable. Right? Very easy. It's very easy. Right? So therefore, try to do the electronics question in the exam because scoring marks is easier if you know the theories. If you have a solid theory knowledge about electronics, scoring marks is easier. Right? Okay.